Guys again, second time. This is my yeah. How you guys doing? Is it fine? It's fine. Yeah. Okay, so we are talking about rotation stuff after rotation. Rotation also mentioned about a bit about what is rotation and what we're talking about for today. And yeah, we'll go through this. The hands out. So we'll briefly go through all of it, but not all the questions. Okay, so okay, before we start, so I think we can start with some recap or some review on the location that you might seen it before. Okay, so some questions for from some of the you're talking about the kinematic, right? Kinematic equations for linear motion, and we're talking about now we are talking the rotational stuff. Rotation stuff we can uh it's like something is uh analog to the kinematic equation that we've seen before, like u plus uh, the constant acceleration final velocity u plus. And so for the four equation from the kinematic equation for the linear motion, okay, for constant acceleration. Okay, so there's some of the stuff maybe you want to go through it again. For the kinematic equation for the rotational stuff, constant angular acceleration, and which means that the power alpha is a constant. Okay, and maybe you want to recap again about what is the torque defined in the vector way. Okay, it's not a magnitude way. Yeah, I want to go through uh, some of the vector kind of the vector analysis also. So we'll go through some of the derivation using vector analysis. And what is the tangential velocity that related to one of the object that's orbiting in one center, about the center, and let's say it's angular velocity, and so um, vector r points from the center to the point mass. Okay, so yeah, this will be two questions that you want to recap again. Uh, the vector way. I mean, yeah, these things that you want to keep in mind for the way. Yeah, and also this two is following the right hand rule that you want to let's say you want to find the direction of the tau and direction of the tangential velocity, and let's say you have these two direction of the r and f, and also the omega and r. You can use your right hand grid rule or script or screw rule that you can find the direction of the tau and v lah. Okay, so the you want to keep in mind that the the angle uh, the angle between two vectors theta is either it points toward the two vector points toward a point or points out to the point from the point. Okay, so they want to keep in mind for when you are finding the theta and also the direction of the tau and v. It's quite important. Okay, so and we will go through moment of inertia, and I guess I guess all of you heard about the inertia from the Newton first law. Uh, can you guys give the idea about like why is the inertia? Like the inertia that you're thinking something is moving and then inertia is quick, then not moving. Any idea what is inertia that you are thinking? Uh, when we are talking about inertia, what things that are come. Okay, mass. Okay, related to maths. Oh, it's in Chinese. 改变状态的 Okay, it's translated is to the difficulty of change of the motion, changing of the motion. Okay, okay, it's another how difficult to start talking about that. Okay, okay, it's kind of related to that one. We're talking about moment of inertia I that we will talking about in kind of related to that we are thinking that we have in mind. Okay, so and we'll go back again and we'll come back again with this. Also the rotational kinetic energy about some axis when object is moving is have the let's say one object is moving with a linear velocity, have a linear velocity, then you have the kinetic energy, linear kinetic energy, translational kinetic energy. And something let's say one object is rigid body, ascended body, not a point mass, it's rotating. Okay, rotating, you have the rotational kinetic energy. Oh, this stuff and also parallel axis term will come back again. Okay, so yeah, uh, and what we are talking about is about this stuff and also some collision, rotational collision, precision, and okay, let's say we start with the rotational kinetics. Rotational kinematics. Okay, so okay, yeah, so, yeah, the things that I want to highlight, the things I want to highlight. Let's say we have in high school they say that in high school the teacher will say that your omega and your angular acceleration, the angular acceleration and also angular velocity is a vector. Okay, it's in high school. Okay, let's say you come to a master or PhD, and in the PhD, like master in physics or PhD in physics, and the teacher tell you that, okay, now we want to show that angular acceleration or angular velocity is not an it's not a vector. Okay. So in some of the idea that is we have the true vector and also the vector, fact vector. Okay, we give a fancy terms and the fancy term is we call it pseudo vector. Yeah, pseudo is a fact one. So what is a fact one? Actually, you should come to some analysis. In specific, it's a Fencer analysis. I haven't go through that, but just give you an idea. Um, then you want to keep it in mind also. But then some right. Okay. So like the vector, let's say it's at a linear velocity. Okay. Pointer. Right. Okay. Okay. Yeah. Okay. Let's say you have a vector V and you have this undergoes a reflection. Okay. A vector undergoes let's say velocity undergoes a undergoes a reflection will be a same direction. Okay. So but then it's a if it is a this is a true vector. If let's say it's a fact vector, the fact vector will be undergoes the transformation of reflection. It will be changing of the direction. Let's say you have the rotation here about the axis here the axis let's say and 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 the angular velocity is the points toward the upper direction using your right hand grid rule or square rule. You can find the direction of the omega. And when you undergoes a transformation of the refraction, you find that your vector will change in the into the opposite direction. Okay. So the idea is that want to give you the idea is that the the vector is not just magnitude and direction that we are thinking about, that we have that we taught by the teacher, high school teacher, that um, only magnitude and direction and it's a vector. But then it also undergoes a series of definition, which in the vector space, there's rules that they must follow. So in the exact, uh, they must follow so that they can be defined as a vector. Okay. So and also in mind that when you have the book, okay, let's say we have the angular displacement, we're talking about angular displacement alone, it's not a vector because when you change the direction, when you do some angular displacement consecutively and you reverse the direction, let's say it's a theta one, theta two, and you can try to fit your books, okay, and you'll find that the angular displacement is not commutative. Okay, so that's why the angular displacement we said that it's not a vector, but then the infinitesimal angular displacement is a vector. Okay, and then you find you will maybe you ask why is this so, and you can try to check out this video more about some visual way to demonstration. Yeah, the idea is that when your angle is very small, that kind of infinitely small, the angular displacement become the d theta, right? And it will be follow the series of the definition of the vector space, vector, which is commutative, and this will be good. So that's why we talk about the angular displacement in infinitesimal small, infinitesimal, infinitesimal. Okay, so it's a vector. Okay, there's an idea of that. Um, okay. Now, so we change this will be the angular velocity of the rate or change of the angular displacement, and this will be the angular acceleration, the rate or change of the velocity, which is angular velocity. Okay. Come back again for that one. I want to give some idea about the analog that we familiar with the sub, familiar with the Newton's law. Okay. 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 I think all of us are familiar with the sub with the Newton's law. Okay. So when you are talking about the translational stuff, linear stuff, we're talking about the mass and also in the linear momentum, with the force and the work done, also the kinetic energy for this. When you're talking about the rotational stuff, somehow it's related, somehow it's analog. It's analog to the things that we are doing, like inertia. This one is moment of inertia. Okay. Related to the mass, indeed, it is defined in the ways that, uh, let's say you have the formation, the rigid body, and let's say you're taking the point of the inner, kind of the idea is that inner moment of inertia is related to the mass. Let's say you have a bigger mass, the inertia is bigger, the moment of inertia is bigger. So you want to change in the rotational this location, uh, you have a bigger mass distribution uh, in the rigid body. Then you have more harder. It's harder to rotate the rigid body. Okay, good idea. Uh, mm, So you can say that you can say that this kind of the inertia, normal inertia thing to make the rotation is harder to rotate. The rigid body is harder to keep. The idea is of that. So it means that you should, for the bigger normal inertia, you need more more forces or more torque needed to rotate the body in the same angular velocity. Okay. Also related to linear momentum, we're talking about the angular momentum or the force related to it will be the torque. And in fact, it is called rotational equation of motion. It means that if we given this equation, then we can precisely define, describe the motion. Okay, so we call rotational equation of motion. In first done rotational kinetic energy. So you see the idea of like the linear mechanics and rotational mechanics. So you want to like memorize the equation so you can get this idea to get this equation. It's a form of a back equation. Okay, actually we have a theorem that we have one theorem say that we have the let's say you have the body. Let's say this is a hammer. Okay, you throw a hammer in a projectile motion. Okay, the hammer is not a point mass. It's a rigid body. It's an extended object. Okay, so when it undergoes a projectile motion, you will see it's like it's also a rotate and also a motion, linear motion. Okay, so it's kind of like complicated stuff. But then Charles' theorem says that when you come to analyze this complicated motion, you can divide into two. Let's say we have you can divide into two motion to analyze and add up together. So you can divide into trans translational part, and also the other part will be a rotational part. So let's say we want to think of that. The hammer is a point mass. It's moving a projectile motion. So it's a translational part, and also the hammer also rotating. Okay, rotating will be a rotational part. Okay, we want to divide into two. The, let's say we want to use some points. Let's say we use the point of center of mass. The point of center of mass to take care of these two parts. Okay. So you undergo the product rule and you try to multiply it in product. Yeah, just take them multiply it into this, and you precisely found that you precisely find that there will be three angular velocity. Okay, the total out will be which is we want to find this as right, not angular velocity is acceleration. Okay, this is what we want to find for the acceleration. Is this one will be the center of acceleration of the center of mass, acceleration, angular acceleration, and also the centripetal acceleration, which is defined you write in the magnitude form, you found it omega r. Omega. So yeah, and also in circular motion. Yeah, by the way, you guys have any questions? You No question is, if any question is feel free to uh, okay. So for the circular motion, let's say we have the point mass moving, rotate in about an axis, about an point origin thing. So because it's acceleration, because the acceleration is defined in the vector way, and although want to keep this in mind, is that although the velocity is not changing magnitude, but the acceleration, the direction is changing. So that's why I have the acceleration because of the direction of changing of the direction of the velocity when it's doing a circular motion. Okay, so yeah, and you can find it that way. Yeah, and if you want to talking about the centripetal centripetal acceleration. Okay, so about you thinking about another term, maybe centrifugal acceleration. They want to keep they came into your mind, and then you are analyze the things. When the thing is when you analyze the thing in when you are in a non-inertial frame, there'll be the centrifugal acceleration instead of, and also there will be some extra forces to speed the bit of acceleration that we when we are talking is we are in an inertial frame, and basically it will be the centripetal acceleration. Okay. Okay, so another idea for question you can try on the questions. If you pause again, which of the questions do you uh, like the questions that must try it before your before your competition. So, yeah. And also we will move on to just now we're talking about the kinematic stuff. Okay, kinematic stuff is not the things that are not involving the force. Now we want to apply some forces uh, and want to apply some forces on top the analog of the forces of the rotational things stuff is about the top, but now we want to hear about the dynamics. Okay, so it's something about the forces they want to analyze. And forces and will lead to the momentum. Like let's say a thought will lead to the angular momentum. They want to find on that system also, and how we can define that things in our when we are analyze a problem. Okay, so yeah, when we are talking about the rotational things, it could be the that's how it could be the point mass rotate about an axis. Okay, so let's say we want to talking about the extended object, which is we call it is a rigid body, and there will be some condition that you might to define on the rigid body condition, define on the what is a rigid body, and let's say we have any 2 points, the distance of the 2 points, uh, let's say Ri, you know, the A, B, the distance between 2 points is always constant. So there will be the rigid body condition that we are idealizing. Okay? So means that we cannot, so means that the body is not cannot be compressed, cannot be pulled in the and deform it. Okay, so we are talking about this stuff, rigid body. Okay, so yeah, the angular momentum when we are talking one of the mass, when talking one mass, uh, or one point of the object, and you're trying to draw a rigid body from the R uh, about this axis. So you want to the vector R. Okay, let's say so this mass, after this body, rigid body is going to take into this direction. So it has the tangential velocity of the linear velocity is in this in the next direction in that instantaneous moment. Okay, so we can define it as mm, this will be we can define the angular momentum will be uh, you draw a point to that point in distance, the position vector, and cross with the linear momentum. Since you have the linear velocity at that mass, okay, at that point mass. Okay. So this will be the stuff about the let's say it's a point mass. The rigid body is just a collection of this collection of many point masses. So we have the Ri, Pi. Okay. And if you want to add them up together and the summation of all the masses, the angular momentum of all the point masses into together, and will become a rigid body. Or that will be the when you add up together, will be the angular momentum of the rigid body, angular momentum of the rigid body as whole. Okay, you're doing a summation and you're doing some this will be the infinitesimal of the linear momentum of the point mass in the rigid body. And when this infinitesimal small, infinitesimal, yeah, there will be the integration part of um it will become an integration. Okay. So and also we know that can express P, there is a P, I want to differentiate ADP, it will be MdV. Sorry, N. Okay. Because you consider the mass will be the infinitesimal small. So it will be the infinitesimal masses. Okay. Can substitute into this relation into two forms. Okay. That's why we define the torque. Okay. And we also say that about the forces is for the linear motion or linear motion, translational motion. The F is equal to P over dt, linear momentum of it. Okay, so we want to analog on that. So we the torque related to the angular momentum. Okay, so okay, so and assuming that this will be the constant, so this one you can pull out. So it will be the differential of the there's a thing we talk about just now about the normal inertia. The inertia stuff is like resistance to the force, or we want to let's say the rotational things. It's a more resistance to the torque to change in the motion. Resistance to the change in the motion. They will be that we talked about just now. This again. And also, for example, it's like you have a mass with uh, M and also another mass, another object with a 10 times bigger mass than others. Okay. So it means that you want to achieve the same acceleration. You let's say A is a constant. You want to achieve the same acceleration. You need for this object, you need 10 times bigger for the forces. Okay. So it's kind of like you want to talk about the torque is related to I alpha. I want to take the magnitude on it. So just consider magnitude. If you want to you want to maintain the angular acceleration in the same manner. Okay, let's say you have the total mass of the two different rigid body. One is 10 times bigger, moment of inertia is 10 times bigger than the another one. So let's say it is the 10 times bigger I, so means that the 10 times bigger torque needed to maintain the same, uh, to keep these two things in the same angular acceleration. Just an idea of that. Okay. And if you want to be precise, right, to be precise, for I mobile inertia, uh, we can generalize this into the tensor. Okay. So a tensor is just a things, just a mathematical stuff we apply in physics to keep our life simple. Okay, to keep our life simple. So physics is life simple. Okay, so it's just like the just a bit explosion explosion yeah, explosion stuff. The rank zero, the tensor will be rank 0, 1, 2, and we are talking about the this one rank 2 will be the matrices we are talking, mm, appear in this moment of inertia tensor. Okay? So it's just a zero, it's like the zero dimension, one dimension, two dimension, three dimension stuff. Okay? Rank 0, 1, 2, 3. That's the tensor. That's a very brief idea of the tensor. Okay. Uh, okay. Yeah. How the tensor make life simple? Uh, instead of writing instead of writing these matrices, and you just write it I alpha, you just write it in a tensor form. I forget the terms about alpha. So you just write in, it's, it's more neat way lah, to for it to in the equation. So it's like more beautiful in that in the physics equation. So physics is more about the beautiful of it. So more neat is means that it's more beautiful. It is some of the idea of why we use a tensor in the physics. Yeah, it simplify our methods of the issue in the in the University of Physics. Everyone still okay, right? Hope that you okay. Okay, so the cross product you want to this will be the cross product you want to then some very we define it, let's say we have the one over n v square, right? We define the vector way, let's say n, because it's a magnitude, right? Magnitude square. It's a magnitude square. So how about we take it as the dot product of it, the dot product of it, two of dot product is just a v square. Okay. So and that's why it defined this way. So we from the magnitude form of the kinetic energy, we define the vector form. Okay. So that's why we want to define the vector form, so because we can apply our equation in it, then we see it before for we go to cross out. Okay. You, and let's say it's not translating for this, it's just our baby object. Okay. So square of it is it's just like you take this vector, it a bit messy. So this is got two product, two vector. Okay. So let's say this will be our result. You're going through the vector cross product, you define it omega will be the S, omega Y, the Z, and R will be the RX, RY, RZ. You're going through the omega cos R, and you write in the proper way in determinant form, let's say omega S, omega Y. If you memorize the formula of the hospital, just proceed it. What I, uh, what I memorize is the, the determinant of this object. So we can get this now. Okay. And okay. So you dot product will this two vector dot together will be precisely this thing, and you define you remember that it will be r perpendicular square or rx ry, right? Square, f square, and r perpendicular square of the n that's then normal inertia. Okay, to get the rotational kinetic energy. Okay. So the idea is that it come with a rigid, let's say the body, rigid body is rotating, okay, with tangential velocity and defined in this way, which is defined in this way, and you go through the vector analysis, vector things, vector stuff, and you get the rotational kinetic energy will be defined, will be related to the perpendicular square, which is defined in uh, I omega square half of it. Okay. Another way you can try to define it or derive it, you can go through the work energy theorem. Okay. In the translation, in the rotational analog. This one, yeah, this you can go through this derivation if you wish to. This will be the cancellation because of this is defined as the normal inertia of the on the center uh about the center of mass. Uh, okay, some of the questions maybe you want to try out. Uh, maybe you can try out this question one. Uh, just the idea of that. Some of the idea of that we want to hear about. You try to analyze. Let's say you have a go through this problem. Just gives you the idea of how to. Let's say you have a mass and uh, some of a wheel radius r. Okay, the wheel cannot move, cannot translate. Let's say it cannot move in a single term. Okay, cannot. I mean, cannot. It can rotate, but cannot translate. Okay, cannot move away, upside down. Okay. So, but then it can rotate really. Okay, so the moment inertia, let the moment inertia, MOI is the moment inertia of the wheel be the I with respect to the longitudinal axis through its center. And there will be the moment inertia about this center. And we want to find the acceleration of the mass. Okay? Acceleration of the mass, assuming the strain remains at all times. Okay. When we are talking about, just want to keep in mind that we are talking about the string stuff, right? Let's say you analyze the things that you object in this pulley. Okay. attached to a string. Okay. Usually the string we are talking about is we are talking about the idea is the length of it is not changing. Okay. The length of it is not changing. The idea of solving this problem, like we keep this in mind that when the pulley or when this pulley or the wheel, the wheel is rotate in a distance, let's say you initial axis is here, and rotate through a distance r theta. Okay, let's say the radius r. Okay. After some moment, okay, if after some moment you release the mass m, okay, you want to keep this in mind that the length, the changing of the length, that let's say the mass is travel L distance, okay, starting from, let's say starting from here, the mass will travel distance to here L. Okay, so um the length that the arc length that the pool the wheel is rotate the arc length is equal the arc length that wheel rotated and also the mass is moves downward. Length of it is equal. Okay, so we are talking about the conservation of string. Okay, so you want to keep it in mind that the length of it is the same, and you're trying to differentiate two times. Okay, because it's r is constant, right? Differentiate two times, actually will be the a equal to r alpha, which is alpha will be the angular acceleration, and this will be the translational acceleration of the mass activity. And this will be the useful stuff that you want to substitute for that equation for the acceleration of the mass that you want to find. Okay. You try to consider the torque and also the F equal to NA, the forces that act on the mass, and also the torque about the torque the torque about is about the gas. And the second method you can try on is the second method is try to consider the angular momentum and the torque of the whole system about the axle, okay, which is about this center. If you can try it, example problem, oh, yeah, problem Maureen, oh, yeah, and let's say this will be if you have time, if you curious about how does it come from, and this will be we call it about the quotient integral, Gaussian integral, okay, and quite obvious, quite how is it, quite quite useful. The integral quite useful in the quantum mechanics and other stuff are actually quite useful when you're talking about this integral. Okay, so actually there's some trick to find the solution of that Gaussian integral. Okay. If you want to check out this video, you can try to check out this video in a visual way, in some visual way to find the solution of this integral, this Gaussian integral. Okay. So another thing that I want to talk about the questions on okay, later we come back again for this question. Okay. Another thing that you want to keep this in mind, come into your mind about you are talking about the locational stuff is about the gyroscope. Okay, myself is to be honest, myself is struggle about I'm year one in university physics. Why you talking about the gyroscope? Gyroscope, how does it work in the physics way. Okay, so when you want to check out this video, actually this video is quite helpful, and some of the video will to the ways that talking about the gyroscopic precision, which you can find it in your phone also when you are when you are in how about it? In some of the apps they want to using use the gyroscope also gyroscopic precision to find the like to far out. Okay, so the idea is that for the gyroscopic precision, like let's say you have an object, okay, you are wall, you hang out this thing, and this is the wheel. You can rotate it. Let's say you see this in this will be the anti-clockwise direction. Okay, rotate in anti-clockwise direction. So you found that when you are not rotating it, obviously the object will be because there is a gravitation pull, right? The object will be fall down. Okay, will be fall down in that way. Okay, so when the thing is not when the wheel is not rotating, when you are rotating it, you will find that it's a weird phenomenon. You try if you try to not fall down like like the like just now, you try to rotate wheel. Let me try to repeat again. You try to rotate the wheel in the anti-clockwise direction or clockwise direction. Okay, you will find that the thing is will not fall down. Okay, but then it will be sustained in the moment. You try to rotate, and the object will rotate in this way. Okay. So there will be some precision. Okay, the precision is okay. What is the precision? Okay, precision is like the change of angular moment. Okay, and perhaps precisely you're talking about the weight of the object. Yeah, the angular velocity of the angular velocity. Okay, so the angular velocity, sorry, the there will be some angular momentum points over this direction. Okay, so yeah, so let's say we have the this one R, right, and it will be the force, and you want to find the direction of the angular momentum. Okay, the direction of the angular momentum. Okay, R is defined because the angular momentum is in the same direction of the omega, right? So okay, you can use your right hand rule. You can try to find the direction of the angular momentum. Okay, so you'll find that you will be in the direction of the cos. Okay, cos then you go to that, and you see from the top. Let's say you see from the top of the thing is the cos. Okay, so let's say we have a high. Okay, want to the idea is that you want to give the idea very difficult. The idea of that is when you're talking about the large inertial angular momentum points in that direction. Okay, okay. and you rotate the wheels, rotate the wheels. Um, there'll be some changing of the angular momentum. Okay? So, and there will be the change of the angular momentum. Let's say with the rotating of the wheels points in that direction. Okay. So the change of it will sustain it in that motion of the when you turn the wheel to will be that will be a direction of the rotate of will be the rotating that will try to sustain it not falling. Yeah. By the way, let's can check out this video and more visual way to get there. Okay. So also the other thing they want to keep on thinking, we we have the things about the parallel axis theorem. Okay. The parallel axis theorem. Let's say we have a moment of inertia about 1 point, let's say S, and it's equal to the I moment of inertia about the center of mass plus mv squared. Let's say we have this object. Uh, okay, let's say it's the center of mass is here, and this other point x is here. The moment of inertia of the about this x is equal to moment of inertia about the center of mass plus mv squared. Okay, it's a particular distance of this v. Okay, mass which is the mass is the total mass of the object. Okay, this is about the parallel axis theorem, and you can derive it in the front part, I think. It's this. Okay. Okay, it's about the parallel axis theorem, and there'll be other things that we call it as a perpendicular axis theorem. Okay, its idea is that perpendicular axis theorem we want to check out. Let's say we have object a flat rigid body lies on the xy plane. Okay, let's say it's x y. Okay, it's a parallel to the x-axis, y-axis, and that sits on for the moment inertia z, y, and so let's say we want to consider the moment inertia about x-axis. Okay, because the exact is it's not it's because it's a flat one, right? So that you can ignore it, that you can ignore it, and you want to try to find the moment inertia of about the y-axis. Okay, you find that this will be the equal, it will be equal. Okay, and now you want to try to find the parallel normal inertia about the axis. Precisely will be the can is add up integrate s squared dm plus integrate y squared dm will be the precisely if plus the what. Okay, normal inertia x about x axis plus the normal inertia about the y axis. So these two things add up together. Okay, so maybe you want to try to think that yeah, how we can apply this in the here, right? I mean in the real problem. Okay, we consider because the object we are consider most of them is not it's not 2D two-dimensional things, right? It's not a flat one only. Let's say we want to consider things that have the same cross-sectional area. Okay, the 3D object, the rigid body, 3D rigid body. And you want to try to find start with the in the moment inertia of the object. Okay, we start with the proper definition of that moment inertia. Okay, and we want to consider because it's a three-dimensional body, right? And we want to consider dx, dy, dz, triple integral. Okay, triple integral x squared plus this is the x squared plus y squared. And let's say this will be the volume density. Okay, the volume density that we are of the rigid body. Okay, so when you are because here, right, and this should be the they try to multiply it this together, it will give you um, area density, the mass density, okay, mass per area lah. To define mass per area on A, and this will be the and because B, right, you can write it as dx, dy, dz, but you can write it another way also because it's the same cross-sectional area, right? There'll be a uniform cross-sectional area. So you can write it in this way. Say we multiply it this with this, and you can write this way. Uh, and and you want to be perspective on x. Okay, so and you'll get this stuff where you are trying to simplify the triple integral to double integral, okay, to double integral, okay, and this will be our dm, and you'll find that when an object have a uniform cross-sectional area, you can squeeze it, you can squeeze it into a two-dimensional things, and with this equation that we can find our normal motion. Okay, starting from motion. Okay. And this will be our from the perpendicular axis. I think the others you can go through again this, and but then you want to come back again to this. Okay, the other problems that you want to try out. Uh, okay, take another 4 minutes, 5 minutes, 5 minutes. Okay, so let's say you have the problem that initially is you have a object, a letter, and wall is parallel. Okay, uniform letter. Initially is motionless parallel to the wall, and you try to put some forces, push some forces, put, apply some forces. Okay, or slight close up, push, and then it will be fall down, right? Okay, but then it's not in equilibrium thing that we happy to see in this problem with this equilibrium and try to analyze what is N1, what is N2. It will be a very easy problem. There's another thing that I want to is a thing. This is the problem that they want to try your. They want to test you is in continuously fall down. Okay, want to consider want to try to consider the try to find the angular acceleration, angular velocity, and also the angle at which the letter is fall down, right? Fall down. At some point, the if you lost contact with the wall, and what is the angle? Okay. But then it's still it's considered as a simple problem also. And you try to analyze the usual way, okay, using the F equal to NA, the net forces NA. Also, you want to in the rotational things with net dot equal to IA, I alpha. Okay. You try to consider this translational stuff, and also the angular stuff of this. Okay. The x direction in x direction, let's say for translational stuff, because it's two-dimensional problem, x direction and y direction, about center of mass, let's say it's about this point. And we know that mg is always acted on the center of mass if it's a uniformly distributed method. So you try to analyze from 2 points of view, 2 ways, two perspectives. Okay, so you'll get the answer of this and this. And the idea is that when the letter is lost contact, right, the left the letter is less lost contact. The force, okay, the force will be zero. Okay, the force that supply it will be zero. So and there will be the acceleration of about the s of this acceleration s taking about the center of mass to be zero. So there will be the condition when it letter less lost letter lost contact with the wall. Okay, so yeah, um, yeah, I think the others you can try out with this or the example you can have to see you're trying to solve it problems try to also yeah and also the rotational collision cells is another thing we are talking that we talked before about linear collision and you want to apply in the rotational cell will be the rotation collision we can try to see it also at other collision other yeah okay perhaps you have uh, more you are more to like do the questions and you prepare yourself in hand and also prepare yourself into the competition or you want to you are more when you are eating something you want to check out some funny video or first check out some interesting video you can have a chat with people maybe some tail talks uh, I think I'm not sure if you guys have getting on the two the problem about the two different friends. Okay, so yeah, um, here will be the stuff that we are talking about. This will be the stuff that we are talking about for patients. Yeah, mean, I think it will be any other question, any thing that um, no any questions. I think our lecture will be until here. Jing, do you have anything you want to add on? And Okay, so here will be end of our sessions for session. Okay, so here will be seeing you guys. Some of you guys are in the hope. Okay, so and yeah, pretty partial camp. I will not be alone. Enjoying the camp, so enjoying the physics. Most important is enjoying the physics. So yeah, thank you guys for your 1 hour to listen my spoken English. Okay,
All right. Thank you, Jinho. I'll start recording now.